Okay, hello everyone. Let us continue the second part of today's class. Okay, in the first part of today's class, we have said that between D and E follow straightforwardly from matrix properties and are addressed as problems at the end of the chapter. Okay. Under the zero mean independent assumptions for the noise, which results in RZZ having the form given by equation 2.24. Okay, let us see 2.24, equation 2.24. RZZ is equal to sigma squared times INR. Okay, so equation 2.26. Okay, this is equation 2.26. Okay, the h of z is equal to nr over 2 log 2 of 2 pi e plus 1 over 2 log 2 of the determinant of RZZ bits. So equation 2.26 simplifies to the following. H of z is equal to nr over 2 log 2 pi e plus 1 over 2 log 2 sigma squared times INR. Okay, in the next section, section 2.7, we are going to evaluating h of r, that is the entropy of the received signal vector. We now derive an expression for h of r that maximizes the MIMO capacity expression in equation 2.21. Okay, let us see equation 2.21. Okay. In equation 2.21, the MIMO capacity is equal to the maximum of h of r minus h of z. That is the entropy of the received signal vector minus the entropy of the noise vector. And the maximum is over Ps of S1 to Snt, okay, where S1 to Snt are transmitted symbols. Okay, Nt is the number of transmit antennas. So this is the joint probability density function of S1 to Snt. Okay, to do so, we appeal. Okay, what is appeal? Let us see the handout. Okay, page 94, problem 1. What is appeal? Solution: a request to the public for money, information, or help. Okay, so to do so, we appeal to the following theorem that is proven in reference 18. Okay, let us see reference 18. Okay, reference 18 is Thomas M. Carver and Joy A. Thomas. They written a book of which the title is Elements of Information Theory, 2nd edition, widely serious in telecommunications and signal processing, Wiley Interscience, 2006. Okay. which we refer to as the entropy maximizing theorem, EMT. Okay, let us see this theorem. Theorem 2.3, entropy maximizing theorem. Let X be a real-valued random vector where the expectation of X is equal to a zero vector, and Rxx is equal to the expectation of X times X transpose. Then h of X, that is, the entropy of X, is maximized when X follows the normal distribution with zero mean vector and the covariance matrix Rxx, where n of 0 Rxx denotes a multivariate Gaussian distribution with zero mean and covariance matrix Rxx. Okay, this theorem implies that h of R in equation 2.21. Okay, equation 2.21 is this equation. Okay, we have seen this equation several minutes before. Okay, it's maximized when R follows the normal distribution of a zero mean vector and the covariance RRR, where RRR is the covariance matrix of the vector R. That is, when R is a multivariate Gaussian random variable with zero mean. Since R is equal to H times S plus Z, okay, R is the received signal vector, H is the channel matrix, S is the transmitted signal vector, and Z is the noise vector. And Z follows the normal distribution with zero mean vector and the covariance matrix RZZ. Then, for a given channel matrix H, these requirements are met if the transmitted signal vector is a multivariate Gaussian random variable with zero mean. Okay. Under this assumption, R has the same distribution as Z in equation 2.26. Okay, let us see equation 2.26. Okay, in equation 2.26, the h of V, that is the entropy of the noise vector, is equal to nr over 2 times log 2 of 2 pi e plus 1 over 2 times log 2 of the determinant of RZZ bits. Okay, except that its covariance matrix is RRR instead of RZZ. It follows from this fact and equation 2.26k. Okay, let us see equation 2.26k. Okay, is this equation. We have seen this equation about 1 or 2 minutes ago. Okay, that the maximum of h of R is given by the maximum of h of R is equal to nr over 2 times log 2 of 2 pi e plus 1 over 2 times log 2 of the determinant of RRR bits. Okay. Therefore, in order to evaluate the maximum of h of r, it is necessary to evaluate RRR as follows. Okay. RRR is defined as the expectation of R minus mu R, where mu R is the expectation of R. Okay, times R minus mu R transpose. Okay, because R is zero mean. Okay, we can see page 96. R is zero mean. Okay, so mu R is equal to 0. So this equation is equal to the expectation of R times R transpose. And because R is equal to H times S plus Z, so this equation is equal to the expectation of H times S plus Z times H times S plus Z transpose. And we use the property of the transpose. Okay, so we put the transpose inside of these parentheses. Okay, so it becomes S transpose times H transpose plus Z transpose. And the first term remains the same. Then we expand this equation. We will get this is equal to the expectation of HS times H transpose times H transpose plus HS times Z transpose plus Z times S transpose times H transpose and plus Z times Z transpose. Okay, and this is equal to H times RSS times H transpose plus sigma squared times INR. And this is equation 2.30. Okay, how do we obtain this equation? Okay, let us see the blackboard. Okay, because I do not have the blackboard, so okay, let me save this document first. Okay, this is chapter 2, page 90, problem 1, and save to the blackboard of MIMO course. Okay, because I do not have Blackboard now, so I use the Microsoft Word instead. Okay, this is chapter 2, page 100. Okay, and problem 1. Derive the last line of equation 2.30. Okay. Okay, boldface. Okay, let us see the solution. The fifth line of equation 2.30 is, okay, solution. Okay, boldface. Okay, let us go back to the slides and see the fifth line of the equation 2.30. Okay, is this. So I copy this line. Sorry. So I copy this line and paste it to Word. Okay. So I call it equation 1. Okay. So next, because the expected value operator, okay, E and the big bracket and a dot is linear. Equation 1 can be rewritten as, okay, so equation 1 is equal to the expectation of this term. Oh, sorry. Okay, H times S times S transpose times H transpose, and plus, okay, the expectation of H times S times Z transpose, okay, and plus, okay, the expectation of Z times S transpose times H transpose, and plus the expectation, oh sorry, expectation of Z times Z transpose. Okay, I call it equation 2. Okay, then from equation 2.19, okay, let us see equation 2.19. Okay, 2.19. Okay, good. So in equation 2.19, we know that H is equal to this matrix. Okay, so I can copy it. Oh, sorry. I can copy this and pass to here. We know that, okay, H is equal to this matrix. Okay, H11 to H1NT and to HNR1 to HNRNT. Okay, and we call this equation 3. Okay, and oh, sorry, not the boldface. And okay, A should be small a. Okay, and okay, S is equal to this vector. Okay, S is equal to this vector. Okay, S is equal to S1 to SNT transpose. So this is equation 2.16. Okay, so from equations 2.19 and 2.16. Okay, and we call this equation 4. Okay, not boldface, respectively. Okay, so R, okay, respectively. For a given channel matrix H, and Hij, oh sorry, it should be Hij, okay, like this, are constants for I is equal to 1 to NR, okay, and J is equal to 1 to NT, okay. Okay, then, so we first we calculate the first term in equation 2. Okay, then this term is equal to the expectation. Okay, expectation and big brackets and the matrix H, okay, and times the vector. Okay, we need okay, yes, this, okay, 3 elements here, so this is equal to S1 and the vertical dots to SNT, okay, like this, and times a vector this, okay, okay, S1 to SNT, and the H transpose, okay, H transpose, okay, H11 to this should be HNR, okay, this should be 1, and this should be 1, and this should be NT, okay, and it is also HR, HNR NT, okay, okay, like this. So I call this equation 5, okay, like this. Okay, first we multiply H and, oh sorry, not boldface, and vector S together, okay, then okay, then HS, okay, bold face and not italic, okay, is equal to this this vector, okay, so a bracket first, and I need 3 blocks here, okay, Yes. Okay, so first is the H11. Okay, and times S1. And this is the, and etc. Okay, plus and dots. Okay, sorry, it is 25 minutes. Let us take a break.